Good evening. This video is going to look at Chapter 21 of Walding with the one-star review questions at the end of the chapter. Now, the one-star questions, while most of them are at the start of the review section, remember a couple of them will be appearing later on, so they won't be in numerical order. The two-star questions will be in a separate video. Let's get started. So, question 15. Question 15 asks, explain why a balloon rubbed with a piece of woolen cloth might stick to a wall notice board without falling. So if we throw our mind back to what we looked at a couple of videos ago, this is part of the Triple Electric series. So remember, whenever we have objects being rubbed together, there will be charge passed around by movement of electrons, and so one of these things is going to get positive, one's going to get negative. Now, there's two things mentioned here. We've got the balloon, which will be made out of rubber, and we have the wool cloth. So that's the first bit we need to explain. The second bit we need to explain is the fact that it sticks to the wall. Now I'm going to talk my way through it while I use some pictures. If you were answering this as an exam question, you would want to provide a lot of what I'm talking about in terms of actually written response. However, you don't want to overdo it. It is only a one-star question. So I've gone back up to my Triple Electric table on 446 to look at rubber and wool. Now, rubber is very, very low on the affinity of electrons. So balloon has high affinity for electrons, while wool is very far up on top of the list, so it has a very low affinity. So it has a low affinity for electrons. So this means that if we rub these two things together, therefore balloon gets E minus, therefore becomes negative. Okay, so if I was to answer this first part, it'd be something like, well, when we rub two objects together, electrons are passed between them depending on their affinity. Balloons have a very high affinity for electrons, while wools have a very low affinity for electrons, so the wool's going to give up electrons to the balloon. This means that the balloon would therefore become negatively charged. The second part is about sticking to the wall now. Some people would leave it here, but they wouldn't actually finish answering the rest of this question, so you've got to be careful with that. And I'm going to draw a diagram. So let's say I've got my wall, and it's got a mixture of pluses and minuses. And I've got my balloon, which now has an excess of negative from here. So this is the before, and after we bring them close, what we'll find is that the ball is still very positive, because the negatives have run away from the edge of the wall. Remember, negative charges, electrons specifically, can move around. Well, now here, wonky looking balloon, all these negatives rushed over there, just because they want to be close. Now, some of them might push into the wall, in which case we'd still have a difference of charge. However, over time, these would slowly bleed off, and the wall would go back to being neutral, while the balloon would go back to being neutral. The same thing we saw in class. Okay, so something like, if I was to include this in a sentence, I'd be including things like the excess negative induces a positive charge in the wall. This leads to a attractive force. Now, if this was a or a B standard question, I'd include some equations at this point, but it's a one-star question. I think that's more than sufficient in terms of how much writing we've done here. Okay, going back to the questions. Okay, question 16. This one's a lot simpler. State the charge on perspex on both materials if perspex is rubbed with silk. Okay, back up to my Triple Electric series. I should really just remember this, but I don't really to. Oh, sorry, I keep clicking off the damn thing. The Perspex, where is it? 460, that's right. Okay, so Perspex is very high in that list. It's right at the top near the low affinity for electrons. So, low affinity. While Silk is around the middle, so let's go medium affinity. So this is going to want to give it off, so therefore the Silk will take it, and that'll end up being positive, and that'll end up being negative. Okay, nothing particularly in depth in that sort of question though. 17. Explain the movement of charge when a negatively charged Van de Graaff generator is momentarily earthed by touching it. Now, the word earthing in here means that it's connecting it up to a very large reservoir where that excess negative or excess positive won't actually matter. Now, they said that it's a negatively charged Van de Graaff generator. So a Van de Graaff generator is basically a big ball on top of an isolated stick, and we charged up. I have one in the lab, but I need a new generator for it to get it working, which is unfortunate because then I could make lightning, which would be boss. Now, when we earth it, what we're doing is we say we might connect it to another ball that has a wire that runs off to an electric socket or to the machine that it runs off. Basically, it lets the charge flow away. So, what happens to the movement of charge? Well, the electrons move into the earth wire and neutralize the Van de Graaff sorry, Van de Graaff has two A's. Ooh, my thing's being weird now. The electrons move into the earth and neutralize the Van de Graaff ball. Okay, it's all about that little movement of electrons, so it wants to go from areas of high density to areas of low density. 18. Two charges repel with a force of 2.8 times 10 to the negative 1 newtons. If one charge is positive 6.5 and they separated by 0.8 meters in air, what is the value of the second charge? Now, the thing I'm going to keep emphasizing to you, when you're reading a question like this where you need to calculate something, write down your variables first. Don't worry about, well, what equation am I going to use? Write your variables first, because if you've got your variables, you can probably end up seeing the equation. If you don't have anything written down, you just try and think, oh, what's the perfect equation to use here? It won't happen. You've got to do it this way. Alright, so force equals 2.8 times 10 to the negative 1 newtons. So both the C plan do check stuff. This is the C part. A lot of you just seem to want to try to jump to the planning part. We say, oh, this is the strategy I'm going to use. Can't do it. 6.5 times 10 to the negative 6 coulombs. Distance. So distance between the two is 0.8 meters. And we want to find out Q2. Another charge. Now looking at that, we've got force, we've got a distance between charges, we've got two charges. That's telling us we're using Fe equals Kc, Q1, Q2 over d squared. I know I use r squared a lot, but I'll try to match up the letter to what thing is going on here. Remember that r just means radius, because we might be talking about a sphere in space, and if you think about it in terms of anywhere around it, the equal distance away from it, you will get a ball. It's just a bit of basic geometry, so the radius, r for radius, pops up a lot. Let's do our substitution. Actually, let's do our rearrangement first, because let's get Q2 alone. So I'm going to multiply d squared over force times d squared. I'm going to divide Kc over, and then divide Q1 over, equals Q2. And now I just need to substitute. So Q2 equals, the force was 2.8 times 10 to the negative 1 times 0.8 squared divided by 8.99 times 10 to the 9 times, what was it, 6.5 times 10 to the negative 6. Okay, and if you chuck that in, you will find that the answer for Q2 will equal, and I did this earlier with Ari, so I know it's correct, so with Ali, so I know it's correct. We will get 3.1 times 10 to the negative 6. And if we read the question, it says either repel, which means it must be a positive charge. Alright. While the math will tell us that, it is good to just infer these things as well. Question 19. If a charge of 15 microcoulomb experienced a force of 750 newtons when placed in an electric field, deduce the strength of the field in correct units. Okay, so let's write down what we've got a charge, Q equals 15 times 10 to the negative 6 coulombs. We've got a force equals 750 newtons, and we want to know an electric field. Well, that equation stands out as being E equals F over Q equals 750 divided by 15 times 10 to the negative 6. Let's do a bit of quick math. 7.5 times 10 to the 2 over 1.5 times 10 to the negative 5. Negative 2 divided by negative 5 will give us power of 7 times 10 to the 7. 7.5 divided by 1.5 will give us 5. And if we double check our answer there, we find that for 2119 is indeed 5 times 10 to the 7. Now, it mentions correct units. In this case, we could have newtons over coulombs. There is volts per meter, which is another formula that involves electric field, but we've used forces and coulombs, so let's use forces and coulombs. Okay, now 20 and 21 and 22 are all two-star questions. They'll be in another video. Let's go to 23. Oh, I just wiped all my thing is crashing. That's a very annoying thing. Okay, well, I'm just going to keep going with 23. You guys have seen me work it out. You can always scroll back and do it to see the working for that. 23. Find the electric potential at a radial distance of 1.6 meters from a point source of charge of value 8.2 microcoulombs. So we've got our capital Q because we're talking about, well, what's something happening from this charge, which was 8.2 times 10 to the negative 6. We know the distance equals 1.6 meters, and we want to know the voltage. Now, if we scroll back up to look through our formulas here for voltage, we will see that voltage should equal charge times distance, I believe. And if we keep scrolling, voltage equals electric field. Note the one. Here we go. So if we scroll up to the top of page 458, you'll find that the voltage of something equals coulombs constant times the charge divided by the distance. Okay, so that's that formula for when we're bringing something in from very far away, but that's okay in this case, because that's all we care about. What is the potential difference a certain distance away from something? So voltage equals Kc Q over D equals 8.99 times 10 to the 9 times 8.2 times 10 to the negative 6 divided by 1.6. I'm going to chuck that into Wolfram quickly to do the math on that, and we'll see what we get. So I have Coulombs constant, 10 to the power of 9 times 8.2 times 10 to the power of -6. And we're going to take all of that and divide it by 1.6, which gives us an answer of 46,073, so equals about 4.6 times 10 to the 4 volts. Let's see how we went. Our answer for 23 is 4.6 times 10 to the 4 volts. Great. Let's go down. We've got 28, 29 left. Okay, so 2 more questions that are 1 stars. So 28 is our next one. Remember, those other 2-star questions will be another video. What is meant by the phrase, the Earth has zero potential? Research this idea and report the outcome diagrammatically. Okay, so remember, when we talk about potential, we mean what is the difference in electric potential between 2 points. Now, if the Earth is neutral, then it has no potential, it has no voltage, it has no potential charge of pushing electrons towards it. Now, that's something that's a research question. I am going to leave that to you to do. However, go back and check what the phrase potential means, and then maybe type into Google, the Earth has zero potential, and see what you get out of it. Last question there is 29, and I think they just wiped a whole bunch of my pictures. Draw a sequence of diagrams to illustrate a technique for charging an electroscope negatively using an induction technique. Okay, so we want to make something negative. Let's draw an electroscope. An electroscope is basically a piece of metal, and it's got a piece of foil coming off of it. I'm actually going to do it vice versa. Okay, obviously my eraser is bugged out. Let's do it vice versa. So what we want to do is end up with our electroscope. So it's isolated, we have a touch plate, we have a foil, and this needs to be all negative. Okay, which means that the plate needs to be negative as well. How do we make something negative? How do we make a piece of metal negative? That's what induction means, that we're going to make it negative. We're going to have to touch it with something. And that means we're going to have to touch it with something that is negative. Because if I touch something that is negative, then the extra negative charges on it are going to rebalance, they're going to flow onto the electroscope. There was a question earlier in text questions where we talked about touching 2 balls, one with, say, an extra, I believe it was 5 or maybe 10 negative charges, and the other one was neutral, and how they would equalize over the 2 of them. So if I bring something with a lot of extra negatives towards this thing that might be neutral, it will end up, the extra neutral negatives will flow onto it. Okay, and so the step 4, before we touch it, still be negative down here, but up here it'll be positive, and that's what's going to allow it to become negative, because this thing won't be touching it. The extra negative will force these negatives to flow away. That makes the electroscope stand up, and then we have the charge plate here will be quite positive. Now we're going to have 2 rods. Let's say a rod and cloth. And before we saw that, was it Perspex rod? I believe a Perspex rod was. That sucks. Yeah. So, no, not Perspex. We want a rod. Rubber would work, because rubber has a very high affinity electrons. Okay, well, this sucks. So, 29. We have our cloth. Let's say it's wool. We have our rod. That's going to be rubber. And if these 2 touch together, that will end up with the wool cloth being positive and the rod being negative. This is very frustrating, I do apologise. Wool cloth is positive, rubber rod is negative. If we take the rod near an electroscope, that'll be negative down there, that'll be positive at the top. Right. Then if we touch it, that's so some of these extra electrons flow onto it, and then if we take it away, last step, take it away, we end up with our electrode, our electroscope being all negative, that's all negative, and our rubber rod over there might be a mixture of positive and negative, because maybe a little bit extra negative, but because a lot of these have now flown off. Okay, so that's what we call induction, where we have something we charge, we bring in something that is neutral, we give it some charge, we take the thing away. If you want to see this in action, please ask me. I have one in the prep room. We can actually see this happen. It's pretty easy to do. I showed most of the class at one point in time. However, I'm welcome to show it again. Okay, so this is all the 1-star questions. We'll use another video for the 2-star questions. I don't do the 3-star questions. However, there are solutions to those, work step solutions for those on the Senior Physics website. So if you Google the name of the book, you will find those. Feel free to take a look at those, and they're good learning experiences. Thanks, guys. Have a good day.